So minus P1 V1 equal minus P2 V2 or P1 V1 equal to P2 V2. So the work done on the left hand side is equal to work done on the right hand side. Work done on the both are equal. So from first law of thermodynamics, you can simply modify this expression. Simply modify based on first law of thermodynamics. Q is equal to PV equal to U plus work done. According to first law of thermodynamics, since it is adiabatic expansion, Q is 0 del U plus work done. So you can based on this expression, you can apply P1 V1 P2 V2 here. You can write like this. For the left hand side of the reservoir, internal energy will be U1, and for the right hand side, internal energy is U2. So you can rewrite this expression like this: U1 plus W1 equal to U2 plus W2. So U1 plus P1 V1 equal to U2 plus P2 V2. So here, interestingly, U plus PV is nothing but enthalpy of the system. So enthalpy on the left hand side is H1, and enthalpy on the right hand side is H2. So now enthalpy of the system is equal, both the systems on left and right hand side are equal, H1 equal to H2. So this condition is said to be isoenthalpic process. Isoenthalpic process. So Thomson Kelvin experiment was conducted not only adiabatically but also isoenthalpically. That is, H1 equal to H2. Enthalpies on the two reservoirs are equal. So finally, you can write the expression for Joule-Thomson Kelvin experiment, Kelvin effect. That is, change in temperature is directly proportional to the pressure difference, dt equal to Joule-Thomson Kelvin coefficient into dP. So JT, Joule-Thomson Kelvin coefficient equal to dt by dP suffix h. This is the final expression for Joule-Thomson Kelvin coefficient, dt by dP suffix h. Here H stands for isoenthalpic process. See, in fact, after the experiment of Joule's experiment, Joule did not practically detect any change in temperature. And in the case of Joule-Thomson experiment, Joule-Thomson's experiment, Joule-Thomson's experiment also, it is not possible to observe any change in temperature, but it is only possible to observe that change in temperature is not equal to zero. It is only possible by doing this experiment repeatedly. That is, you have to compress the gas, high pressure gas, and allow it to naturally expand through porous plug, and after expansion, then again repeatedly you have to allow the expanded gas to compress and allow it to send the gas to for the expansion through porous plug. So in this process of repeatedly compressing and expanding the gas molecules or air molecules, you can practically able to realize some significant change in temperature or significant drop of temperature in the reservoir too. That is what Joule and Thomson Kelvin observed. But they could not obtain any significant change of temperature in their first attempt. That is, when a gas is allowed to compress and expand in the second reservoir via porous plug, means they could not detect any small change. There might be some small insignificant change of temperature, but practically it was not detectable. In order to realize the significant drop of temperature, we must repeat the cycle. So they repeated the cycle. After repeating many cycles, they could achieve or they could realize any significant change in temperature or significant drop of temperature in the second reservoir. See, this change in temperature from capital T, high temperature to low temperature in the first reservoir, in the second reservoir, leads to the drop of temperature of air molecules, leads to the invention of liquefaction of gas molecules or cooling, gas cooling. So it leads to it is the basic experiment, and based on this experiment only, all the equipments like heat pumps, like refrigerators, air conditioners, all these instruments have been designed based on Joule-Thomson's experiment. So this Joule-Thomson Kelvin experiment is the basic and fundamental concept behind the development or behind the invention of refrigerators as well as air conditioners.